So I've been talking about controls and everything for a variety of systems. I've also talked about a little bit about neural networks. And here I want to talk about ways I think neural networks in these control systems can be improved by using the right function. Briefly, from my previous videos, which I linked, about controls of network, is that you have nodes that are connected. These nodes send signals A, B. These nodes receive some signals first. I'm just going to draw them in here. Do some math, A and B, then they send that math. Once they do some math, they send it to a node higher up that does some more math and stuff. And this math can be like how much it moves the fin, how dramatically, and they can also just sometimes directly move the fin a node. But all of this does some kind of computation which ends up moving a real-world system or doing something in the real-world system. Now, the simplest way of controlling something is either with on-off switch, which I've discussed. And for fine control, if you have just on-off switch, you need many on-off switch. And it also can lead to little leaps in here and there, where this dramatically increases or decreases, which can be okay in some systems if you stay it out, or some systems that are not as how would I say it? Not as a big deal, just not as sensitive. But some systems that can be a big deal. Now the simplest thing that's not just on and off is a line. So that you put in an input and it puts into an equation of a line, mathematically. The problem with a line is kind of twofold. The first problem with lines is that if you have one line and you put into another line, you only get a new line. You can't get any more complex function than line with a line. To explain that, I'll give a couple explanations. One is the mathematical way that all lines are a form of ax plus b, or mx plus b, depending on who taught you. And the a or m is how fast it goes up and down, and the b kind of does the position. Does it start at this point, or does it start at that point? So it moves it up and down the graph or side to side. Then if I put another equation for a line, same formula, and you can do the math yourself, and I put that equation for a line within another line, if I first do that, then I just stupid out, I will actually get another line that's just some value times x plus another number, still equation for line. If I do it infinite times, I'll still always get a line. Another way of thinking about it that's more graphical, which I do down here, is I take a line, and it can start with any line, and if I move one point in a line up using another line, or down, or side to side, I do that for each point, I still get another line. If you put a line like here, drawing here a vector, then I attach another line to the top of that, you can see that I just made a longer line, like a triangle, the hypotenuse. And I just keep doing that, and I'll still keep getting longer and longer lines. For that one, I really do recommend you draw it out or look at the screen. So, lines are not the best unless you think the system is really controlled linearly, or you think it can be approximately linearly. Now, with feedback loops, it can actually be nonlinear, because the environment might not be linear, so that might make the responses not linear, because the environment outside is doing the stuff that's not linear. An example of that would be that if it's responding linear to temperature, but the temperature outside is not fluctuating linearly, then it's going to go up, then went down and up and down, and roughly follow the curve of that of the temperature outside, but with just lines going up, then coming down and stuff, that approximates that curve, like I do here. So what's your next option? And this is used in machine learning, in neural networks, and more. Well, the next simple option that has worked well is rectified linear units, or ReLU. RE from rectified, L from linear, and U from units. And what they did is they just took two lines and pieced them together. So it's one line until a certain point, then it becomes a different line at a certain other point. And there's more complex ones later on that they use many more lines to give it cutoffs or stuff like that, because you might want a function never to exceed 10 or only be triggered at 5. So you can have ones that look more like this or something like that, and many more. But the idea was that this is not linear anymore. You can see that it has, if I do something, a calculation here, it acts very differently than if I do a calculation here. If I put these two lines together, if I add another line like this, I might get a line that zigzags here, zigzags like that. I'll get a double zigzag, maybe, or I can get even more weird responses. I can get, if I put one that curves over here, I might get something that curves faster than even faster. All these other shapes, if I combine them. There is a couple problems though with ReLU. Yes, it's simple to calculate, but look very close to this dot. It's not very smooth, and that can lead to sudden jumps or harder for it to adapt if something is just happening at that little boundary. It's still like the on-off problem. A big jump, and it's not a smooth jump. Sudden turn. And that means your system is sensitive around there. And you can, sometimes if you add more things, it can either smooth out the sensitivity or increase it. That is a very complicated thing to look at. Now, the alternative to that is something, there's many alternatives actually, but an alternative to that is a little more smooth would be any function with a higher power from a quadratic. So x squared plus 1 plus x plus 1, or anything higher, or cubic. And you can also add a and b's and c's and other terms. The problem with all that is, compared to linear, is you're doing fancier math. Once you're doing fancier math, a couple of things always happen. Your system is slowed down significantly because you have to do the fancier math. It requires more actual energy and power to fuel the system because the math is more complicated. You can have less nodes controlling the whole thing because each node has to do more computation, so it takes the place of one or two nodes. Now it can give you more accurate results, so sometimes that's worth it. But it does do that. Another problem with this whole thing is that the more complicated architecture right here means that it might also be less precise because it has to do fancy math. If you're taking a number and you're adding 2 plus 3, it's pretty easy. Timesing it, you get 6. Also easy, but let's say you have a 10-digit number by 10-digit number. Or let's just, if you have 10-digit by 10-digit, you probably could take your time and add them together. If you have 10-digit number, and you will still get roughly a 10-digit number by a 10-digit number. The digits, when you add stuff together, it's usually, if you just add two numbers together, you only can increase the digits by a maximum of 1. But if you times two numbers together, you could have a 10-digit number by a 10-digit number. You can easily get 100 digits. Numbers. A huge magnification amount of computation places, and this leads to a lot of problems with this accuracy and error being introduced and rounding, which makes the whole thing not behave as well. Also, it means more memory because you're storing bigger numbers or doing computation with bigger numbers. So that's another drawback. Now, I think there's an alternative that some people have looked into, but I'm talking about doing this now from the hard wiring standpoint, not the soft wiring standpoint that most people will talk about. So this is all true with computation, theoretically, with just the math. But what if we actually look at what this hardware can actually do? It's something that's used in every electronic, very simple thing called a capacitor. And what a capacitor charges or discharges following a exponential function. So an exponential function is the form of, I wrote EX, but it can be form of A, B, 2 raised to X power, where X is an exponent. So it can be, so if X is 2, it's AB squared. If X is 3, it's AB cubed, and so on and so on. Capacitors just naturally do this, and this is one of the most common electronics, and that's for the discharging and charging so much energy they store and release. Now, because they are common electronic, and they're just and they're also one of the smallest ones, you don't have to worry about all this fancy computation and how to compute it exactly. Electronics just does do it for yourself, and it's just one little piece. So then you save all these computational problems. The second thing that an exponential equation lets you do is that an exponential equation is one of the most smooth equations. By smooth, I mean, here's a lump here where it turns because the derivative changes suddenly, or the rate of change is very sudden. But you can also look at the rate of change of the rate of change and how sudden that is. And you can look at the rate of change and how sudden that is. You can have smoother and smoother curves. One of the smoothest curves is a circle. The straight line, if you continue a straight line, it's a smooth one. But any angle is not smooth, and you can have different ways of looking at how smooth it is. It turns out these exponential functions are super, super smooth and nicely well behaved when you look at derivatives and stuff like that. But they can increase very fast. Another thing is a nice non-linear property about them is that there's a lot of things you can do to modify it for particular systems once you understand it well. You can flatten out any section of the curve, which I do here. So instead, it only acts as exponential during part of it. Another part of it is just flat, same number throughout. You can have it have jumps with simple electronics. So it just doesn't, it goes from one value straight to another value, or stops. You can stop the curve early on. You can zoom it in, more magnify it. So instead of being 10 and 100, it could be 100 and 1,000 very easily. And these are all with modifications with just 1 or 2 extra components that are all nanoscale. Or you can make it go up a lot faster. And with all this being very simple, I think this is also would be where we should look at designing the most new neural networks. Because these new neural networks, yes, maybe you could argue whether the curve is the best curve mathematically, but hardware-wise, you can fit a ton of these ones. And the more you can fit, the fancier curves you can fit. Because you have more things that can do it. It's like having, instead of 10 brain cells, having 1,000 brain cells. Maybe those 1,000 brain cells is not as good as 10, but you have 1,000 brain cells. And it will save on, and each one will be more accurate and would save power and memory. There are some issues with what I said. Capacitors are more sensitive to the environment, to disturbances outside, such as voltage fluctuations, power fluctuations, and are more sensitive to the magnetic field and electrical field outside than transistors. So that will be something to look into. It might mean that sometimes the more linear ones would, in some cases, be better. Well, thank you for listening. Please like and subscribe. It really helps the channel out. I'm trying to reach 1,000 subscribers in a year, 4,000 watch hours, which is really hard, but with your help, I think I can do it. Also, if you have any ideas for future videos, comments, or suggestions, leave them in the comment section below. Thank you very much. Goodbye.